Wouldn't it be nice if you could program a 3D printer as easily as this?
What should we print?
Well, let's see. Ooh, coffee mug.
Well, too bad that's not how 3D printing works. This is how it really works. Okay, that also isn't how it works. Well, at least not yet. Today we're going to give you 7 simple design tips for metal 3D printing. Welcome back again to Star Rapid, the company that does serious engineering for serious engineers just like you.
Serious engineering.
First of all, why metal 3D printing? Metal 3D printing allows you to create highly complex designs that are lightweight, strong, and ideal for applications such as motorsport, aerospace, and medical. To get the most out of metal 3D printing, you need to adhere to certain fundamental engineering and design rules. Tip 1. Optimize the process. Just as you wouldn't expect to throw a complex sheet metal part at a sand casting foundry, you should not expect to throw a typical CNC machine part at a metal 3D printing company. So if you don't have experience of designing for metal 3D printing, you really should speak with your supplier before you start to design your part and get their advice. Tip 2. Put your part on a diet. There are 2 fundamental types of metal 3D printing technologies out there. The first is a laser or a beam-based technology, and the other is a multi-jet printing technology. Nowadays, most laser or beam technologies are used to melt powder to make an almost 100% solid metal part of the correct size directly in the printing machine. Most multi-jet printing technologies, however, use a kind of resin to bind particles of metal together, and later, in a secondary process, the resulting parts are sintered. This usually results in a 50% shrinkage by volume, which doesn't necessarily mean that they are inherently inaccurate, and I've personally found that the shrinkage is quite predictable. The build time for laser-based direct metal melting technologies is very closely related to the volume of the material used, and to a lesser degree to the height of the build, whereas the multi-jet printing with sintered technologies are pretty much the opposite, with height of the build being the main consideration and volume being a secondary one, except for the cost of the material itself. If you want fat parts making, then multi-jet and sintering is probably the better option. But if you want to get really accurate and almost 100% solid metal parts with very high strength, you're going to need to put your parts on a serious diet and keep their weight to an absolute minimum. There are many awesome 3D CAD systems out there which can help you do this kind of design, and 2 very good examples would be Autodesk's Fusion 360 Generative Design and Altair OptiStruct. These kinds of systems evolve the design through multiple iterations, mimicking the efficiency of nature, allowing you to use the absolute minimum of material. Tip 3. Metal 3D printing is not a CNC replacement. Too many people expect high precision from metal 3D printing, and although the precision of these technologies is way better than it used to be 10 years ago, it is still not precision machining. Typically you can expect plus or minus 0.1 to 0.2 millimeters, but this is not a hard and fast rule. Parts can buckle and twist due to the design or the volume of the parts, so you can occasionally see parts as much as 1 or even 2 millimeters away from CAD. It's rare, but it does happen if the general rules of metal 3D printing are broken. We strongly recommend using a secondary machining process if you want to achieve any features that are high precision, and often do this for our customers. Tapped holes, reamed or bored holes, and certain critical faces or features can all be done after printing. This way you get the best of both worlds. Impossible to machine structures with a few high precision features only where needed. Tip 4. Don't go too far with the dieting. Just as being too fat is not good, being too thin can also be problematic. We strongly recommend that you keep wall thicknesses greater than 0.5 millimeters, otherwise the features can distort due to the temperatures involved. Tip 5. Holes, slots and gaps. Keep your horizontal or vertical round holes, slots or gaps also bigger than 0.5 millimeters, otherwise they will just fuse with the opposite wall and cease to exist in the build. Tip 6. Large overhangs. Keep any overhangs in the part below 0.5 millimeter if you want to avoid us having to use fillet supports, which are expensive to remove. If you've noticed, there is a 0.5 millimeter theme going on here. You can see from our test samples, when we create a horizontal square or rectangular hole, the wider the hole is, the more likely the flat ceiling is going to collapse due to a lack of support in the powder bed. To avoid this, think Roman architecture.
All right, but apart from the sanitation, the medicine, education, wine, public order, irrigation, roads, a fresh water system and public health, what have the Romans ever done for us?
You can have rounded or sloping ceilings to counteract the effect. Sloping ceilings are by far the most efficient and can be used up to the very largest holes because the 45-degree slope is totally self-supporting. Whereas the rounded ceiling starts to break down when you get to above 4 or 5 millimeters in width. Tip 7. Self-supporting structures. I used to personally run plastic 3D printing machines, and taking off the supports from a plastic stereolithography part was frankly child's play compared to getting the supports off of a laser melted part. It is very common that companies like ours use a fast EDM wire eroder to get the main supports off, and then we have to use rotary grinders and other industrial tools to get the rest off. Now that is serious engineering.
Serious engineering.
No, not there. No. Wait, later. I know you like it. I've got it. The building and removal of supports for the laser melted parts costs time and money, so we strongly recommend avoiding designs that require them in the first place. This is actually possible if you understand the metal 3D printing process. You can design the part such that it is totally self-supporting in the Z direction of the build.
Who's Zed?
Zed's dead, baby. Zed's dead.
So long as all the walls are greater than 45 degrees to the horizontal, they will be self-supporting and not require additional supports. Now, using a design given to us by Renishaw, we build bottle openers as giveaways. I have to say, it is one of the most beautiful and efficient designs I have ever seen. No one we know has ever broken one, and yet not only can we support these parts with just one single tiny support, we can even stack them in a laser melting machine. That's the perfect, utterly self-supporting design, and that's why I love to show it off. See below for a fabulous article all about the universe that is metal 3D printed bottle openers from Metal AM magazine. The first 100 people to get their request to us using the email link below can have their very own DMLM 316L stainless steel bottle opener with their name built into the side of it. We can have up to 11 characters in your chosen name, including the spaces. And finally, tip 1 again. Always talk to your supplier before and during your design process, pretty much for anything. Well, that's it for today. Hope you enjoyed it. Go ahead and destroy that like button, subscribe, and share this video, or Johnny will get you.
Here's Johnny.
And as always, we are the company that does serious engineering for serious engineers just like you. Yeah, now.
Serious engineering.
Side effects include serious loss of weight, keeping your gaps and holes open more than 0.5 millimeter, avoiding all of those nasty to remove and expensive supports, and being able to support yourself even when your now super slim part buggers off with another designer and leaves you with the invoice.
Watch this.
Reconstruction complete.